Okay, so we are on Chapter 4 of An Introduction to Statistical Learning. We are in the conceptual questions, and this is question 2. And question 2 is discussing linear discriminant analysis. And the text states that, that this expression right here, expression 4.17, which is in the book, if we classify observations according to this expression, that is equivalent to classifying them according to this expression right here. Okay, so let me talk a little bit about these. So what is this expression up here, the top one? This is the probability that a particular observation, X, belongs to the category K. And then all of this is Bayes' theorem, where pi k is the prior probability of category K. This whole mess here is the expression for a normal distribution, a univariate normal distribution. Okay, and so here it serves as the likelihood for Bayes' theorem. Okay, and then down here we have what's called the marginal distribution, which is the sum of all of the probabilities for each category here called L, okay, all the way up to the capital K categories. Okay, so again we see the numerator basically duplicated, but now summing over every possible category from 1 to K. Okay. And so if we classify observations by the Bayes classifier, we are told that that is the same as classifying according to this delta function here. Okay, so the value that has the largest value of P is the most probable category for X, and similarly, the value or the category for which the delta function is the greatest is the most likely category for X. Okay, so we want to prove that that is a true statement, that by classifying by the delta function is the same as classifying by Bayes' theorem when the likelihood is assumed to be a normal distribution. Okay, so the way that I'm going to do this is to, so delta is some kind of log transformation of P up here. And so the way that I'm going to do this is to show that delta K is proportional to the numerator. I think I said likelihood in the text here, but it's the numerator. In fact, I'm going to pause this and fix that once I finish this thought. But that delta K is proportional to the numerator of the Bayes classifier. Okay, and in the Bayes classifier, the category with the greatest numerator is the most probable value. The marginal distribution does not matter when we're just ranking the possibilities, the possible categories. Why? Because every one of these expressions for P of K has the same marginal. So when I'm comparing them, they just cancel out. Okay, so again, it's the numerator, the value, the P with the greatest numerator is the most probable value for, or the most probable category for X. Okay, let me pause this for a second. Okay, so we're back. So let's just start working on log transforming this this Bayes classifier here. So just one little thing that I noticed. So the question asks in log, and I am using the natural logarithm, so I'll denote log by ln, but they're the same for our purposes here. Okay, so let's just start by simplifying the Bayes classifier. Okay, so I have the prior probability, and then I have all of this I'm calling fk of x. Okay, so that expression right there is just our normal distribution formula, and then the marginal, all of this stuff down here, I'm just calling capital M, right? So M again is just the sum of all of is the sum of the products of all of the priors with their corresponding likelihoods. Okay, so it looks like this. It turns out that we're not going to have to mess with M much at all, and that should make sense because like I said, the marginal is irrelevant when we're just ranking the most probable categories here. Okay. So now if I take the log of this expression here, I get this. All right. So the log of the Bayes classifier is the log of, well, so I guess I don't have to read it out for you. Okay, but this is what we get. And then we need to go about expanding this middle term here. We're not going to do much with this term because, like I said, it's not going to matter. Okay, but I'm going to expand the log of the likelihood here. Okay, and that's what all of this is doing here. And so you can walk through the steps yourself. Okay, but in the end, what we get is this expression right here at the bottom. And now if I look at this expression, I recognize quite a few terms that were contained in delta. Okay, but it seems like there's more terms here. All right, so what are the terms? So the terms that are contained in delta that are also contained here in this final expression are precisely the terms that somehow reference category K. Right. So again, I've duplicated delta here. Okay, so the log of the prior for K, that's part of it, right? So that expression is right here. Okay. Notice that this expression right here doesn't reference K, and it's also not in our expression for delta. All right. This does not reference K. It's not in our expression for delta. But now these final, or these not quite final, but this term and this term do reference K, right? So we have the mu of K, okay? And these are referenced in delta. Okay? And then why did I put Lm there? It should be Ln of m, okay? Ln of m, the log of m, is not in our expression for delta, okay? So again, the values that make it from our final expression to the value, or for the expression for delta, are precisely the ones that are referencing K, okay, category K. And this should make sense because if I'm trying to distinguish among the different categories, well, then the only terms that are going to make a difference are the difference that are distinguishing among the different categories, right? So for instance, x squared over 2 sigma squared, well, all expressions for delta, or I'm sorry, for the log of p, are going to have that exact same term in there, and so they're just going to cancel out. It's not going to be relevant when we're comparing these different categories. Okay, that is it for this.